Okay, good morning everybody. Let's get started. We are working our way through the last open problem in evolutionary robotics. How do we scale up evolutionary robotics so we have an ever-increasing number of human participants that are helping to exert evolutionary pressure on a population of robots? We looked last time at a project from my group, Twitch Plays Robotics. This was an attempt to include large numbers of non-experts. They don't know what evolutionary robotics is. They may not know what a robot is. They don't know what a fitness function is. So can we connect human participants with evolving robots through natural language? So throughout this course, we've touched on a lot of the building blocks of intelligence. When we started this course, we tried to define intelligence, and actually defining precisely what intelligence is turns out to be a difficult thing to do. Most approaches in AI and robotics these days attempt to basically build one building block of intelligence after another into a machine. One of those building blocks, of course, at least in terms of human intelligence, is understanding and generating natural language. That problem itself is also an open problem, and the Twitch Plays Robotics is one approach to tackle that. We're going to switch gears today and look at another project from one of my previous graduate students, the DotBot project. So there's a different way to combine computers running evolutionary algorithms with human participants and evolving robots. And we'll talk about the DotBot project in a moment. Just a little bit of scheduling. I'm going to be traveling at the end of this week, so I will not be here on Thursday. Instead, you will have your third and final guest lecturer, Nick Cheney. Nick was an undergraduate here at UVM a handful of years ago and took this class. He went off and did a PhD at Cornell and a postdoc at the University of Wyoming, and is now back here on the UVM faculty as a research assistant professor. So he will be here to talk a little bit about the work that he's doing in his lab, which has a lot of overlaps with evolutionary robotics. Okay, you're now the undergraduates are moving on to your third weekly report. Hopefully you've got into the rhythm of these weekly reports. As you can see in this weekly report, this is my third stepping stone towards my final project. And what I tackled this past week was X, and here are a few images and videos of X. Pretty straightforward, right? What you probably figured out, the way to be successful in these weekly reports is to really think carefully about your final goal, which may be more or less ambitious, and really thinking carefully about how to break this down into bite-sized steps. I've been giving you a few hints and tricks along the way here to think about ways of doing that. Another one I'd like to tackle today is fitness function development. Some of you are far enough along that you're starting to develop non-trivial fitness functions, and they can be a little bit difficult to get to work right. So typically, start with a single term. So we've seen a lot of work so far where you're simply maximizing distance. Some of you are doing projects where you're evolving two populations of predators and prey, trying to create simulations where you put into that simulation pairs of robots. It can be difficult to get all these pieces to work and make sure that you're still computing the correct fitness for a given robot in a simulation that may contain more than one robot. So as you start to build up your fitness function, you might start to develop more terms, but you want to make sure that those terms are actually in there in the right way, and this can be a difficult thing to figure out. So it's very important to debug and be able to visualize all the steps on all the steps on a pipeline that are going from the end of a simulation to collection of the results from the end of that simulation. So when the simulation ends, it gives you back that data structure called results. And then from results, you can pull out specific sensor data. And when you pull out sensor data, you're getting back a NumPy vector. So that vector is going to have n elements in it, where n is the number of time steps in the simulation. If you're working with more than one robot in the simulator, then obviously some of the sensors will belong to robot 1 and some of the sensors will belong to robot 2 in results. a lot of problems crop up in where you think you're pulling out the third proprioceptive sensor in robot 1, but you're really pulling out the first proprioceptive sensor information in robot 2. So make sure you're getting the right sensor data from the right robot. How do you know that you're pulling out the right sensor data? The easiest way to do this is, for example, if you pull out of the sensor data touch information from the left foot of the first robot, for example. You've got a vector t, and it's a binary vector. Every element in that vector, if it's 0, represents that that foot in that robot was not on the ground at that time step. A t equals 1 at that point in the vector represents that that foot was on the ground at that time step, and so on. Easiest way to debug this is to just throw the vector into the fitness function. You can't throw the whole vector in, so the easiest thing is to take numpy and take the mean of the entire vector. Call this t prime just for now. If this is my fitness function and t contains touch information from one of the robots, and you run this fitness function for a few generations and play back the best robot at the end of a few generations, what do you expect to see?
Nothing really. It's just going to stand still.
Stand still, why?
Because it's going to want to maximize the amount of time the left, well, I guess only the left leg's on there.
Exactly, right? So watch the simulation, and the first robot's left leg better spend most of the time, if not all the time, on the ground. 1 over 1 plus t prime. Run it for a few more generations, and you should see the first robot keeping its left leg off the ground for as long as possible. You don't need to run 300 generations, but this is a relatively simple fitness function. It should take only a few generations until you can see in the simulation that you have correctly pulled out the right sensor from the right robot, and so on. Right? Sort of one of the nice things about having the physics engine is you can sort of visualize the results of most of your code if you think carefully about how to do it. Okay, any other questions about PyroSim final projects? No? Okay, so back to scalability and crowdsourcing. As I mentioned, we're going to talk about the DotBot project today. We want to combine lots of people and computers running evolutionary algorithms and evolving robots. Our participants are going to be non-experts. So where are the different points in an evolutionary robotics experiment where we can include human non-experts? As we saw in the Twitch Plays Robotics project, one way we can do that is through natural language. Humans are instinctual teachers. We teach our pets, we teach our children. We have sort of some built-in software about how to teach learners. Where else might we be able to include human participants? In the DotBot project, we relied on humans' intuition about biomechanics. So as you can see here, the human participant is connecting the dots in the right panel. And by doing so, they're creating the morphology of the robot. So in the DotBot project, we told human participants that you can create robot bodies, and AI will program the brains of those robot bodies. In a couple weeks' time, towards the end of the semester, we're going to look at evolutionary algorithms that are evolving morphology and control. We've already seen a few of those experiments already. Is designing the body more intuitive than designing the neural controller? That's something we want to investigate in the DotBot project. Okay, so after the human participant creates the robot body, it simulates it in, this is actually the Bullet physics engine, and there's a JavaScript version of it called Bullet.js, which has the nice property of running directly in the browser. In this case, whenever the human participant creates a robot body and clicks go, the computer creates a random controller for that body, drops that controller into that body and into the physics engine and runs it. In this case, the fitness function is fixed, which is locomotion away from the origin. This particular body-brain pair gets about 1 less than 1 unit away from the origin. Oh, sorry, that's time left. Gets a little over 3 units away from the origin. Okay, is that a good robot, a bad robot? Who knows? At this point, the participant can either click the go button again. What do you think happens when they click go for the second time for this robot?
One step in the evolutionary time step.
One step in the evolutionary algorithm, whatever it is. In this case, we just used a simple hill climber. So the first time a robot body is constructed, a new hill climber algorithm gets created and associated with that robot body. The hill climber starts by creating a random controller for this body, which you just saw running. If the participant hits go again, it creates a randomly modified copy of that controller for that body, runs it on that body again. If that second controller gets the robot further away from the origin, we keep that controller and throw away the old one. If it travels less far from the origin, we throw that one away and keep the original parent controller. Alternatively, the user can click reset and build a different robot body, in which case a second hill climber is constructed for that robot. A new random controller is created for that second robot body. The user can click go and continue and so on. And so now we have, so far, a single human participant constructing multiple robots and generating multiple evolutionary algorithms that are associated with each robot. So far, so good? Okay. That's the basic idea. What did we want to test in this project? Well, again, we're trying to tackle this problem of scalability. How do we actually get more and more people building more and more robots, and in this case, running more and more hill climbers against more and more robots? If we get more people and more computers running more hill climbers against more robot bodies, do we actually do better? Does the crowd collectively discover robot bodies for which it's easy for evolution to find fast-moving controllers? Or is it basically just at the top level random search? We have a chaotic jumble of a bunch of people making robots and hill climbers, and there's no overall synergy or progress. That's the question we wanted to tackle. If we have more and more people, does the entire system that contains people and hill climbers and robots do better in the sense of finding a robot that travels far from the origin? That's what we wanted to tackle in the DotBot project. So the first question we wanted to know is, do people work well together? If people are observing each other creating robot designs, are the people learning from each other about what robot body plans work better than others? So if you came to this website, you could, as you just saw, create your own robots, but you could also see robot designs created by others and how well or how poorly those robots were doing. So this is sort of a graphic about how this algorithm works. In panel A here, we have user 1, participant 1. Participant 1 draws this robot body plan, then clicks go, and then we have their computer, user 1, participant 1's computer running a hill climber. The colored lines here just represent a controller. They run an initial random controller, which gets the robot to move not very far from the origin. Participant 1, again with their computer, clicks the go button again. A second controller now runs on the same robot. The robot travels a little bit further. While that's happening, participant 387 is watching the designs on the website and sees this particular design getting a little bit better. So participant 387 redraws this design that they've seen, and they click go on their computer, at which point the hill climber associated with this robot continues on computer 387. So there's one hill climber associated with every robot design, but that hill climber may be run on multiple computers as more and more people start to focus on this design. So far, so good? That's just one design. Participant 2 is watching all of this occur and says, this design is flawed. It's not going to ever work very well, so I've got another idea. Participant 2 comes up with this design, and she clicks go on her computer a couple of times and gets her design to travel this far. Participant 1142 is observing participant 2's effort and contributes some more computational effort, and so on. Participant 1 eventually gives up on his design over here, watches the progress being made on this design, abandons their original design, and makes a variation on this design. Todd.
Is the hill climbing distributed across participants with the same body design?
Exactly. So anybody who creates the same body design, we query a central database and it pulls out the hill climber associated with that design and continues the hill climber at that point. So the more people that draw the same design, the more computational effort that hill climber receives. Make sense? Okay. Multiple robots, multiple controllers, multiple hill climbers, multiple human participants. Okay. In this case, we have everyone observing each other's designs, and as you can see here, participant 1 was influenced by observing the designs made by participant 2. Is that social dynamic, observing the designs of others and either contributing to those designs or making variants on those designs, is that social dynamic helpful? Helpful in the sense of, as more and more participants come to the website and play the DotBot game, in the system as a whole, if we look at across all the robots in the system, which is the one that travels the furthest from the origin, does that get better the more people that participate? Any ideas? If you put more and more humans together in a team and give them a collective project to carry out, do they get better at doing that task? I'm sure you've all participated in some teams.
It depends. There's kind of an optimal number of people on the team.
Exactly, right? Doing things by committee sometimes works, sometimes doesn't. Depends on the task, depends on the number of participants, depends on all sorts of things. In this case, does it work? Right? There are positive social dynamics like creative synergies, right? Aha, this design seems to be working. Are there variants of this design that we might try, right? There are positive synergies in social dynamics. There are also negative antagonistic dynamics going on in a social group that's trying to carry out a collective task, like in this case, find the fastest moving robot. What are some of those pathologies of collective work?
Once you see someone else's idea, it's hard to think of your own.
Once you see someone else's designs, it's hard to think of your own, right? Groupthink starts to set in. So I picked this, when we made this figure, I did it deliberately. You've all seen the quadruped by now, and you all might think this is a pretty good design. Given the interface that you just saw, which is connecting pairs of dots together, is the quadruped design you just saw optimal? It's a loaded question, right? Probably not. Any ideas what it is? All right, save that one for a little while. Okay, let's pause here, and I'm just going to skip ahead. I want to talk a little bit about what's going on under the hood. How are these robots actually constructed? Well, as you saw, we tried to make a simple interface that most people would understand, connecting the dots. So in the interface, you can click on a dot and drag to another dot and let go, and it then connects those dots. In this simple morphology here, made up of these two edges, the moment the participant clicks go, every connected node becomes a small cube in the simulator, and every edge becomes a cylinder that goes from one cube to the other. We then connect this cube to this cylinder with a rotational hinge joint, and this cylinder to this cube with a rotational joint, and so on. So unbeknownst to the participants, when they are connecting the dots, they are actually specifying the positions, orientations, and numbers of objects, and also the joints that connect them together. So far, so good. In this project, there are no sensors, so we're going to use open loop control here. As you remember, in open loop control, we have a standard sinusoidal pattern, and that sinusoidal pattern is going to be fed directly to the motors. You'll notice in this video that not all of the joints are rotating in phase with one another. Some of the joints are out of phase with one another, and some of the joints are in phase with one another. If they were all in phase, they'd all be rotating upward and inward towards each other and then flexing away from one another, in, out as a whole. That's not what you see. So what the hill climber is doing when it's creating the controller is setting the phase offsets of all of the joints in the robot. So we've got objects, joints, no sensors, just motors. All the motors receive exactly the same frequency oscillation. The only difference between the joints is their relative phase offset. How does the hill climber determine those phase offsets? Well, when somebody creates a design like the one that you see here, this creates 1, 2, 3, 4 joints. So we need to specify the phase offsets for those 4 joints. We create 4 triplets in the genome, as you see here. So you have a genome which is of length 12. For each triplet here, the left-hand digit is either 0 or 1. 0 represents it follows 1 point in the frequency, and a 1 represents that it's out of phase with all the joints that have a phase offset of 0. So we don't have continuous phase offsets. There are some of them that are set to 0, some of them are set to 1. So all of the joints that have a phase offset of 0, those all oscillate in phase with one another. All the joints that have a phase offset of 1, they all oscillate in phase with one another. And the 0 and 1 joints, they oscillate in antiphase to one another. That's the controller. So far, so good? Okay. As you can see here in the DotBot interface, we have 1, 2, 3, 4, 5, a 5 by 5 set of dots. So we have a total of 25 dots. How many possible robot morphologies can be constructed?
Are we not counting robots that are equivalent to each other when they're rotated?
Exactly. So all rotational and positional invariants are ignored. So if you connect this dot to this dot and create a small snake bot in the upper left, or you connect just this dot to this dot and create a small snake robot in the bottom right, from the point of view of the system, those are different robots. How many possible robots can be made?
2 to the 25th.
2 to the 25. So we need to consider whether each edge is present or not. So we have 1, 2, 3, 4 possible edges in the top row, 4, 8, 12, 16, 20 possible edges. 21, 22, 23, 24 possible edges, 28 possible edges, 32, 36, 40 possible edges. How many total robots are possible?
About a trillion, 2 to the 40.
2 to the 40, right? So about a trillion, more or less, possible body plans. For each one of those trillion or so body plans, how many controllers are possible? A little bit more tricky calculation. No one in my lab has been able to sit down and work this out, so if there are any people here that are interested in combinatorics, we would love to know. We know there are 240 morphologies. For each one of those morphologies, there is at least one controller. Some robots, like this one, have a very large number of possible controllers. Smaller robots have less. The total number of robots and controllers in the system, we're not sure. Okay, leave that as exercise for the reader. So far, so good about the setup. Okay. So as I mentioned, we're testing this hypothesis to see whether putting more and more people together on this task produces faster moving robots. So in this setup, people can observe each other's designs, and to see whether that fact that they could observe and build upon each other's designs helps, we created a control experiment. In the control experiment, everything is exactly the same, but now users cannot see each other's designs. So over here, participant 1 builds this robot and evolves the hill climber on this robot for a little while. Then they abandon this design, come up with a different design, run the hill climber for a little while on this design, come up with a third design, and so on. While they're doing that, in parallel, another user is coming up with their own designs and exerting computational effort on finding controllers for them, and so on up to the nth participant. If by chance one of the participants creates a design that is created by another participant, that participant takes over that hill climber at that point, but doesn't know it. So they're working more or less independently. We can then ask the question, as more and more users participate in this way of building robots or this way of building robots for the same number of participants, the same amount of computational effort, which human group produces faster moving robots with more or less the same computational budget?
What's your metric for which group does better? Is it the best performing robot between the two, or all of them together, or something?
The best robot found by the group as a whole, right? You have, we tell the group, well, we don't tell the group, but unbeknownst to them, they have 1 million iterations of a hill climber across as many computers as possible. Find the best robot with that amount, with that computational budget.
And along with the design, they can also see how far the robot went.
They can they can see how far the robot went in the interface here. So not just how far the robot went, but how it actually tends to move.
But if they choose someone else's, so if they're able to see someone else's robot, that's also included.
If they see somebody else's design and recreate it and click go, the hill climber will take over from that point. And if that hill climber has run for quite a while on that design, it'll probably continue off from where the performance seen for the other participant.
Do the human participants know what they're trying to accomplish as a group, or are they just there to experiment and play around?
Good question. So this is important. What are the instructions that we gave to the human participants? We told them it's a game, and the game is to try and create the best robot possible, where best is get the robot to travel as far from the red dot as possible. And the more you click go, the more the AI that's running on your computer has to figure out how to get this robot to move. So they, assuming they read the instructions and more or less understand the instructions, they know that there is an AI running on their computer that is trying to animate their robot to move as far from the origin as possible. And if they play for a while, they'll notice that it's harder for the AI to make progress on some designs than others. That's all they know. Question?
So to confirm, if someone builds a robot someone else has already built,
Yes.
it's already been evolved a little bit.
Yep.
And did that cause a problem because they kind of thought that robot was like really good compared to others that had evolved?
That's a great question. So in the independent group, this one, if they by accident create a design that's already been tested by someone else, they might suddenly see that that design is doing very well immediately. Whether that had an effect or not, we're not sure. That's a good question. That might have been a confounding variable in this population. What's that?
I think I designed that exact same far right.
Oh, very good. Okay, maybe that's your design.
How how are all the different genomes stored, the different hill climbers? 'Cause I feel like the more participants you have, the more robots you're gonna have. Like, that's a lot of, I guess, storage and computation.
The storage is trivial, right? Because it's basically just binary information. So we have the 40 possible edges. So we're just basically, in terms of storing the design, it's a binary vector of length 40. It's pretty small. And then associated with each of those binary vectors is another binary vector, which may be shorter or longer, that contains the controller, right? That's basically it. We don't need to store the hill climber. All the hill climber needs to do is read in from the database the current best controller, which is the parent controller, and then that hill climber runs locally on the user's machine, makes a randomly modified copy of the controller, and repeats it, and so on. So in terms of total storage, it's not that big. Question?
Well, I would say, are you still asking which one would do better? I would say probably the collective one.
You're an optimist.
Because, well, it's almost, I think that's a version of transfer learning, right? Because if you look at all the symbols and you're like, oh, this one does really well, they're not going to waste time on the ones that don't do well. But at the same time, there's a lot of people out there who would just look at the interface and then just start drawing lines everywhere. And so in that case, you might add more noise.
So it's a good point. So again, we're hopeful that there are positive synergies, that people will see good designs and contribute more computational effort to those good designs and abandon early non-promising designs. That's the positive side. But the negative side is if you get too much of that, you get groupthink, and you have too much computational effort on good designs, but not the not yet discovered optimal designs or better designs, right? So if you look at this system as a whole, the social group can get trapped on a local optimum, which is a good body plan, but not the best body plan. And I'll preface that by saying we don't know what the best body plan is. Question?
So I have a couple questions. My first question is, if the robot is the same as another robot, but it's somewhere else on the grid,
Yes.
is that considered unique?
Those are different robots. Yeah, absolutely. So we didn't build in anything to look for positional or rotational invariances.
To run this on the user's machine, won't they need to install PyroSim, in your case, PyroSim on their machine first?
It's the bullet physics engine running in JavaScript in the browser, so they don't need to install anything. Other questions? Yes?
When doing this, has any, you know the secretary problem?
I do not.
Well, the idea is that when you're looking for a candidate to fill a job, there's an optimum amount of time you can spend looking for the right candidate.
Okay.
If you go too far, you spend too much time.
That sounds like a variant of this problem, right? So what is the optimal amount of computational effort that should be thrown at any given design? We don't know, but we're hoping that the group implicitly figures that out. Okay, so we have two groups at the moment. As I mentioned, we have the collaborative group and the independent group. There's a third treatment or a third variant of this algorithm that we're going to run, which is the machine group. In this case, no humans allowed. We're just going to create a bunch of hill climbers that are going to search the space of morphologies and controllers together. So now the genome in this hill climber is a 40-length binary vector, which represents the body of the robot, which of the 40 edges are present or not. And then associated with each of those vectors is this control vector, which represents which subset of joints within that design are moving in phase and which subsets are moving out of phase with one another. So three teams: the collaborative team, the independent team, and the machine team. Who wins? The machine team. The machine team is in red. The machine team lost to the humans. Way to go, humans. Let me just describe the axes here. So horizontal axis, as usual, is evolutionary time. It's not represented in number of generations because we have different hill climbers running for different numbers of generations. So we took all of the evaluations done in the simulation. So one simulation is one evaluation. The total number of evaluations performed by each of the three teams together. So for this team, there were, in this cartoon, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 18, 27 total evaluations for this team. At that point, after 27 evaluations, what was the fastest moving robot in that team as a whole? So far, so good? Okay, so we ran this for about a month, and the green represents the independent team, and the blue represents the collaborative team. Okay, as you can see, after about a month, we shut off the independent team system, and everyone who came to the website after this point could see each other's designs, and they were all collaboratively working together. And we wanted to see, as we just let this experiment run, how well could the collaborative team do. Okay, so if you were a human participant in this experiment, what did you see when you came to the website? This is what you saw on the website, and I just showed you the drawing interface and the simulation interface. If you were in the collaborative team, you also saw this weird-looking high score table at the top. And if I zoom in a little bit on this, these are it's a collection of designs at the moment. This T-robot up here, it might be difficult to read, has traveled so far 25.95 units away from the origin. So this is a pretty fast moving machine. This one traveled 4 units away, this one 2 units away, this one 1 unit away, and so on. So you can recreate one of these designs or create one of your own. That's what you saw if you came to the website and you were placed in the collaborative team. If you came to the website and you were placed in the independent team, you saw everything was exactly the same except this bar at the top was missing. You just didn't see anybody else's designs. Okay, question?
Yeah, so they were randomly put in a team, I'm assuming. So what happens if someone closed their browser and then came back? Would they then be put in a different team?
Good question. So when someone arrived at the website, we collected the IP address, flipped a coin. Heads, they're placed in the collaborative team. Tails, they're put in the independent team. If they come back and we see the same IP address that's in the database, they get sent back to that group. If it's a different IP, they get sent to a different group. It's possible that some of the participants running this on different computers had different IP addresses, and they might have actually ended up in these different groups, and you'd get treatment pollution, right? We're trying to create these 2 different treatments that have this difference between them, these humans collaborating, these humans working independently. There may be a little bit of pollution where a small subset of users ended up in both groups. I'm pretty sure that that was a pretty small number. Probably not 0, but small. Okay. Why did the collaborative team do so well?
Looks like they made like breakthroughs.
Okay, absolutely. You can see that there are periods where not a lot happened and then there were breakthroughs. It's not clear whether it was the humans that made the breakthrough, that came up with the new design, or the hill climber eventually found a much better controller for the same robot. But this definitely wasn't incremental improvement. There were periods where not a lot happened, and then there were sudden jumps.
With the robot in like the 4th square where it's 3 different T's, is that one robot or is it not connected?
This one?
Yeah.
Exactly. So from our point of view, there are 3 small robots in there. From the hill climber's point of view, it's still all one robot, but the 3 parts of the robot are mechanically independent. Okay, so the collaborative team won, and we kind of know why, because clearly they sort of riffed on each other's designs and exerted more computational effort on more promising designs. It's the only really explanation we can come up with. But what were those promising designs? Here are some of the, at least to the right here are some of the better performing designs. There are some common features among these designs. What are there? If you were to randomly connect, or if you were to randomly draw a subset of these 40 edges, you get certain patterns, and the ones created by humans are far from that random distribution of random body plans.
They're symmetric.
They're symmetric. That's the first thing that jumps out to most people. We did not tell the crowd, make symmetric designs. We've actually run this independently multiple times again. With new users, they tend to converge on symmetric designs. Why?
I'm just curious if the machine team came up with symmetric designs that were the best as well, because I feel like human bias would lead us to make.
Here are the best designs made by the collaborative team, best designs made by the independent team, and the best designs made by the machine team. Pretty easy to distinguish between humans and machines in this case. These machines are not going to pass the Turing test in the context of the DotBot. Why do the humans converge on symmetric designs?
Well, our own bodies are symmetric and most creatures are symmetric.
Absolutely, right? So remember the original hypothesis. We're trying to include large numbers of human participants in the endeavor of creating robots. In the Twitch Plays Robotics project, we were relying on humans' instinctual abilities to teach. In the DotBot project, at least the original hypothesis is that we can exploit humans' natural intuitions about anatomy and behavior. Remember our discussions about biomechanics when we were talking about legged locomotion and bipedal locomotion? It may seem obvious to you, but if you have an asymmetric body plan, it is very difficult to move efficiently in a straight line, right? If you've ever had a limp, you are at least temporarily asymmetric, and it takes a lot more effort to move in a straight line than when you don't have a limp, right? I don't know whether the human participants were explicitly thinking about that. My guess is a lot of that was sort of subconscious, right? So people are able, although they're not formally trained in biomechanics, it seems we can sort of draw out their intuitions about what kinds of body plans afford fast movement compared to a set of participants that do not yet have those intuitions. What else can you tell me about the human designs? Are there other features other than symmetry?
They're simple. They use lesser, I guess, cylinders or dots.
They're simpler, right? So these, as you can probably imagine, all these pieces moving, they mechanically antagonize with one another. We talked last week or 2 weeks ago about positive and negative interference, right? One piece moves up while the other piece is pulling down, and vice versa, right? They may be working at cross purposes.
With a simpler body plan, don't you also have a much smaller pool of controllers to sample, so you can find your maximum?
That's also probably pretty helpful, right? So the crowd seems to be converging on symmetric designs, simple designs. Although it's not clear here, they're also converging on designs that are made up of one component. So there's a few exceptions, like this one here, as was pointed out. This one has 3 separate components in it, but generally speaking, the crowd tends to create a single component. All of the top designs from the machine team here are also single components. But if you look at a larger set of the good designs produced by the machine team, there are a lot of them that are made up of lots of multiple components. Okay. That's the end of phase 1 of the DotBot project. So we have evidence suggesting that people work well together, they synergize, and they tend to converge on, or they tend to use their intuitions about motion. They converge on symmetric designs, which taken together allows them to trounce the machine team. Okay, that's all well and good, but this is still a pretty effortful enterprise for the human participants. It takes a while to draw these things, test them, look at designs being created by other humans, redraw them, change them, and so on. So in phase 2 of this experiment, we're going to switch from crowdsourcing, pulling out designs from the crowd, to crowd seeding. In crowd seeding, we're going to take all the designs created by the humans and try and distill them down to useful features like symmetry and simplicity, and give that design feature to the machine team. We're going to give the machine team a hint that is a distillation of the human's intuition about this problem, and see whether the machines can digest that intuition and use that intuition and do what machines do best, which is search a much larger space than the humans would ever be capable of doing, right? So we're going to try and bring together the best of both worlds. We're going to distill down and incorporate human intuition into a machine team, and then rely on the best ability of the machine team, which is brute force effort. Okay, how do we do that? As I mentioned here, we picked two features that were common among the fast-moving human designs and were absent from the slow-moving human designs. Each square here represents a subset of designs. The darker the dot, the more designs that exist at that point. And the position of the point in the horizontal axis represents how much symmetry is in that design. And the vertical position of that point is how many components are in that design. As you can see here, most of the designs had high symmetry and were one big connected component in the DotBot interface. Okay, so we distilled this down to a fitness function, which combined symmetry and the number of connected components. The fitness function was symmetry, which is computed as a value between 0 and 1. And we then multiplied this by 1 over 1 plus the number of connected components. We know that actually we can just do 1 over, it was actually S over C because we always have at least one component, right? So the fitness function, when we run the machine team again, is now going to be maximize symmetry and minimize the number of components. That's the first objective. The second objective is move as quickly as possible away from the origin. You'll recall a couple weeks ago we talked about multi-objective optimization, or MOVE, right? Where we're trying to combine both objectives, and the evolutionary algorithm is trying to push points up and to the right on this Pareto front, where it's trying to maximize this and maximize distance from the origin. So far, so good? Okay. So we ran the machine team again. Blue here represents what I just showed you. This was the machine team of just computers, evolving morphologies and control, and at the end produced designs, good designs that traveled a little more than 15 units away from the origin. We then reran that machine team with multi-objective optimization, and it did a little bit better. Not a lot, but it helped. So this suggested to us that there's promise in this approach, that we actually can distill down human intuition and incorporate it as an objective in the fitness function. So in essence, what we're doing in this phase 2 machine team is saying, create good designs, but do it in the way the humans would have done it. So far, so good? Okay. Here are some of the designs that new machine team came up with. Doesn't look like it, but they're pretty symmetric. They're not all single components, but most of them are. The machine team said, there you go. I've created some good designs like the humans do. Perverse instantiation, right? Did what we asked for. Maximize symmetry and minimize components, more or less, but not in the way humans did it. What's missing?
Simplicity?
Simplicity, right? Okay. All right, symmetry, number of connected components, and simplicity. Now we've got everything, right?
These just kind of look randomly put together, whereas all the human designs had patterns.
These look random. The humans have patterns, right? What do we mean by patterns? We're put in symmetry, minimize components, try and make them simple. The humans look non-random. What do we mean, right? At this point, when we were conducting this experiment, we hit a wall. So we'd finished phase 2. We had proof that you could actually include human intuition to make the machines do better, but we were clearly not capturing the full scope of human intuition. The humans were doing something in these designs that weren't just captured by symmetry and number of connected components. We also put in symmetry, simplicity, helped a little bit. We seem to be missing something. So I'm going to describe phase 3 now. In phase 3, instead of manually looking, us as the investigators, looking at the human designs and manually trying to pull out features like symmetry and components, we're going to use a machine learning algorithm to find those components for us. So now things are going to get really complicated in phase 3. We're still trying to perform crowd seeding. We're taking all the human designs, we're going to try and distill out of those human designs common features among the fast-moving designs. But instead of us trying to do that manually, we're going to get the computers to do it. Okay. How do we do that? Not surprisingly, we're going to use an evolutionary algorithm. Okay. Here's how this goes. The nice thing about the DotBot project is people are describing the bodies of the robots as networks, collections of nodes and collections of edges. And it turns out there's a big literature on the study of networks. And among that literature, there are lots of different features that describe networks. So we went to the literature and we pulled out a dozen or so features that describe a network. Each of these features here are variables, results in a single number describing a particular network. So for example, let's look at maximum degree here. So if we want to compute the maximum degree, for example, of this network, we visit each node and we compute the degree. How many edges are arriving at that node? For this node, there's 1 edge. For this node, there's 3 edges. For this node, there's 0 edges. The maximum degree in this network is 4. So far, so good. So we can compute that metric for that network. We can also compute it for this network, this network, this network. So for any given robot body, we can generate a whole bunch of variables that describe that body. And you'll see there's symmetry in there. We already talked about that one. Which of these variables most captures the relationship between the body and how well it did in the DotBot project? Hard to say, right? As we did in phase 2, we tried to do this manually. So let's just start with S. Let's say we take S and we compute S for all the robots created by the humans, and we break that set of designs into the fast-moving robots and the slow-moving robots. And we then ask, is symmetry greater for the fast-moving robots than the slow-moving robots? Turns out that yes, there is that relationship. Symmetric designs produced by the humans tend to move faster than asymmetric designs. So there is that relationship there. That's capturing things pretty well. As we just saw in phase 2, S divided by C, the number of components, there's a cleaner relationship now between the performance of the robot and S over C. So far, so good? So we can keep writing down ever more complicated equations that are combinations of these variables and ask how much of a relationship is there between that equation and the performance of the robots. Okay. So on the right-hand side here, we're defining a whole bunch of different operations or ways that we can combine these terms. So we could, for example, ask, what's the relationship between S divided by C? It turns out the relationship is pretty good. We could ask, what's the relationship between S times C? Turns out that that's also pretty good. S plus C, not so good. S minus C, not so good. So for any given equation that I write down, we can associate with that equation an R squared value. The r squared value just gives us back a value between 0 and 1. 0 means there's no relationship between this equation that describes a given network and the performance of the robots. An r squared of 1 means there's a perfect relationship. I can tell you exactly how good a robot is going to do if you evolve controllers for it, if you can write down the values of these variables and plug them into my equation. So, question?
So, how did you do the calculation? Like, what were the rules?
Exactly, that's where we're headed, right? So you can imagine now a vast space of equations that are combinations of these variables, and the height of any one equation is r squared. How well that equation captures the performance of the designs should be starting to sound familiar to you, right? So we're going to run a particular evolutionary algorithm which we introduced at the beginning of the semester called genetic programming. Genetic programming differs from the other evolutionary algorithms that we've seen in that genetic programming doesn't evolve vectors or matrices, it evolves equations, right? So in genetic programming, we're going to start by creating a population of random equations, reach into our bag of operators here, pull out an operator, and if we pull out addition, for example, addition requires 2 new subtrees to plug into the left and the right side of the plus. We reach into either the bag of variables or the bag of functions and keep going, and we can build up a random equation. Go to the next slot in the population, build a second random equation, third, fourth, fifth, sixth, seventh, and so on. Now we have a whole bunch of random equations. Compute the r squared value for each of those equations. How well do those equations predict how well or how poorly the designs will do? Delete the equations that have low r squared, that don't predict performance. Keep the ones that get high r squared and make randomly modified copies of those equations. So a question about how do we actually mutate an equation. So if we take, for example, s plus c, like you see on the board here, we have a plus at the top, we have s down here, we have c over here. Our equation is being represented in the computer as a tree. We pick a node in this tree at random, like for example, this node, delete what's in this node. We now have an empty node. Flip a coin. Heads, we reach into our variable bag. Tails, we reach into our function bag. And in this case, comes up tails. We reach into the function bag. We grab division. Division requires 2 operands or 2 arguments. So we now place 2 empty nodes underneath. Reach into the bag again. Maybe in this case, we pull out uppercase C and number of segments, uppercase G, for example. Now we have a new equation. Is this one better at predicting performance than not? So far, so good? Okay, so now we got a pretty complicated system. We've got humans, hill climbers, robots, and genetic programming, which is trying to work on, it's working on behalf of the machines. Let's try and figure out what the humans did. What's common across their good designs? Boil that down into an equation that's found by genetic programming. Once we find a good equation, we want to plug that in up here, and the machines are now going to optimize the speed of the robots and come up with designs that satisfy this equation.
Is your training set just the existing data that you've already collected, or? Correct.
The training set is all of the designs produced by the humans, and I've forgotten now what it is, several hundred or several thousand designs. It was actually several thousand. We had quite a large training set. As you can imagine, when we ran this genetic programming, it discovered S. That appeared in the population of equations pretty quickly. S does a pretty good job of predicting performance. After a couple generations, S was killed off and replaced by S divided by C, which was good news because we knew that was what we had been able to come up with. Our ego took a bit of a blow when SC was easily replaced by something else that was better than anything we could come up with. Anybody feeling particularly awake this morning? What's better than S divided by C given these variables and these combinations?
Does it have to do with the number of limbs, maybe?
Number of limbs helps. So limbs are any edges that have 1 degree. So sort of any edges that are sticking off. Limbs help, which again you would expect, right? Limbs are generally useful for locomotion.
Seems like all the human designs had much fewer segments.
Had fewer segments, right? So that's captured by uppercase G here, the number of segments. Yep, that helps. In what combination?
With C. Or not
With
C,
with C and S.
and L.
With lowercase c, right? How do we combine all those variables together? Do we add, divide, 1 over 1 plus, 1 over... Okay, so hopefully you now have the sense of where human intuition starts to run out. Don't feel bad if you couldn't come up with a better equation than S over C. These are the top 10 equations that predict human performance. The performance of human designs.
So back to the building the equation, when would it choose to put in just a constant? Would there be any point where we would throw in a constant?
Are constants on here? I don't see them. There are no constants explicitly that are in here. However, genetic programming can construct constants from this set if need be. How?
Multiply a number by another number.
Well, we don't have numbers, we have variables. So how do we get constants from this? Or how would the genetic programming, let's say it needed 2.5 times uppercase G. That's the best equation. How is it going to make 2.5?
2.5 G over G. Or to get 2.5.
You can't get 2.5, right? The only thing the GP can do is reach into either of these two bags and pull something out from the bag. 2.5 is not in either bag.
You could do something like G plus G over G.
There you go, right? So G plus G over G will give you 2. So you're part of the way there. You can figure out how to get the rest of the way. So if constants were useful, it can build them, which they are. There they are, right? Okay, so GP was creating constants. Okay, that must be a typo there. 0.041, obviously 0.041. How could we have been so foolish to not realize that was useful? Okay, so the error over here represents, again, how good this fit is, this r squared. In this case, we took this equation, which didn't have this one had the lowest error. This was a good fit. It's still pretty high. This error, r squared, ranges between 0 and 1. So GP could not find an equation that had an error of 0.2 or 0.1 or 0.01. It's very hard to find an equation that predicted very well how well a human design would do. Probably not so surprising, right? This is a pretty complex system now.
So did you actually see what the error rate on the S by C equation was? Maybe.
We did. I don't remember what it was, but it's much higher than anything here. It's 0.9, 0.95. So it's very hard to predict, given one of these equations, how well or how poorly a design would do, but clearly some do better than others. Okay, in this case, we took this equation, which is the one that got the lowest error, and we plugged it in as the second objective to our multi-objective optimizer. First objective is maximize speed of the robots. Second objective is maximize this thing. And we handed over those two objectives to the machine team. We handed over that equation to the machine team, and off the machine team went, producing body plans and neural and controllers to maximize those two objectives. The best we had done before with just symmetry, maximize symmetry and minimize components, was this, which is here. We did significantly better now. So what this tells us is genetic programming is better able to distill down from human designs, human intuition. in the form of features that are common across all the designs. But obviously, whatever those features are, they're pretty complex. And if you plug that distillation of human intuition down into a purely automated system that's evolving bodies and brains of robots, does better than any machine team so far. Still not as good as the humans, but getting better.
So is that equation that we found, is that like just for your initial parents, or is that like combined somehow with the objective of moving forward?
So we took the objective one, which was distance. Hopefully that's not there, right? Maximize distance, and then maximize equation one here.
So it has
two objectives. So so the machine team creates a robot with a particular morphology. Okay, we take that morphology and we compute all of the variables describing that feature, which gives us, if we compute this entire equation, it gives us a single value for this equation. We take that morphology with whichever controller it has at the moment, run it in the simulator, and it travels this far away from the origin. That morphology controller pair sits at this position in the multi-objective space. The machine team creates a second body and a different controller, and that ends up at this position. Third robot here, and so on.
When does it decide like to switch bodies and run a different?
That's a good question. I forgot to mention that. So in the machine team where it's evolving morphology and control, every time a design is mutated, we make a copy of that design, flip a coin, heads, add or remove an edge, so make a change to the body. Tails, change something in the controller. One joint now changes its phase. So the machine team with 50% chance is modifying the body, otherwise it's modifying the controller. So far, so good? Okay. Okay, here are some of the top designs produced by this machine team, which is now doing pretty well. So doing what the humans did. Still not yet, so quite a ways to go in this experiment.
Do you know if the parameters that define what the humans did that were, like the machines that the humans created that were successful, also apply to three-dimensional robots if you're doing some pyrosim?
Good question. I don't know. How well does this generalize outside of the very, very simple interface of the DotBot?
Because the point is to be able to extrapolate the human intuition and then not have to use human participants, right?
Exactly. We want to use humans for what humans are best at, which is having an intuition for something, but not necessarily being able to explain to themselves or others what that intuition is, right? So would these common features, these distilled intuitions, would they generalize to 3 dimensions? Probably not, right? It's already pretty high error in the original interface itself. If we transfer to something else, maybe not. But maybe we could replicate this whole process again and try and distill down human intuition when they're designing 3D machines, possibly. Okay. Let's finish off this lecture. What is the optimal DotBot? The T is pretty good, and that was the best. This experiment ran on the web for over 2 years, about 2.5 years. The T lasted for about 2 years, was eventually replaced by something else.
Hexapod?
Oh. You're all hopelessly infected with groupthink now, right? Quadrupeds and hexapods on the mind.
What team found it?
As you can imagine, I often use this in outreach activities. So we go and visit middle schools and show them this, and they play the Connect the DotBot game.
Was it a human found design or?
A middle school student named Olivia. She came up with the design that blew the T-Bot out of the water. And what, Olivia did not create a hexapod, didn't create a T, no quadruped,
Snake?
not a snake. Other ideas?
Yeah.
Did she just draw the entire grid?
Entire grid doesn't work. If the entire grid worked, the machine team probably would have done pretty well. Not the entire grid.
Middle school pen,
Is it a giant rectangle?
Ah. A rectangle or a ring. So this is Olivia's ring. It turns out different rings of different sizes and different major and minor axis don't matter too much. For some reason, this works extremely well. It's not a quadruped, not a hexapod. We were pretty surprised at the time. Olivia did this with 20 or 30 of her fellow classmates who also saw this. They all started making rings, and they pushed everything off the high score board. And unfortunately, the website isn't up anymore, but when we finally shut it down, it was completely covered in Olivia rings. So way to go, Olivia.
Why don't we see animals like this then?
As you may have seen in this course, right, we often try and recreate the products of evolution, quadrupeds, hexapods, bipeds. What we're really trying to do in evolution is not recreate any particular product of evolution, but the process of evolution, right? If you go to BTV, you don't see giant airplanes that are flapping their wings. We don't slavishly copy the way that nature produced heavier than air flight. We very gradually distilled down intuitions about thrust and lift and came up with designs that you don't really see in nature but still work perfectly well. Any other questions about this project? Okay, I think this is a good place to leave things for today. Just as a reminder, you have a quiz due tonight. I will not be here on Thursday. Nick Cheney will be telling you about his work. And I will see you all again next Tuesday when we'll talk about swarms. Thanks very much.